right. How many are still working on the midterm or haven't done the midterm yet? Okay, a few. So obviously we can't go over the midterm if people are still working on it or are about to work on it. But let's solve a few more problems. We're on a streak. So let's do this one. This is from the third problem set. What's the expected cost of a minimum spanning tree over endpoints uniformly distributed in the unit square as a function of the number of points? So what does that mean? So we have a unit square. One by one square. Why 1 by 1? Because it's normalized to some size. If it's larger, then the answer will be proportionally larger. All the answers will be expanded by whatever the multiplication factor, if it's a larger square or a rectangle or whatever. You have a bunch of points. Okay. And we want to create a minimum spanning tree over them. How many know what a minimum spanning tree is? Okay, pretty straightforward. It's a way to connect all the points using an acyclic graph, a tree, such that the total size is minimized. It's minimum size over all possible ways of connecting the points. So there's famous algorithms to do this, Prim and Kruskal. We haven't gone over them yet, but still, we don't need those algorithms to solve this problem. And so you want to connect them as a tree. So what would a tree look like? Well, for these points, a minimum spanning tree could, I'm just making it up here, could look like this. That could be a minimum spanning tree. I'm not saying that's exactly the answer, but it looks something like this. So the question is, what's the cost of this tree, given that these points are random? And by random, I mean uniformly distributed in the plane. Every x, every y has equal probability of being a coordinate of any one of those points. Uniform distribution. How many understand the problem? Just a few. All right, well, I'll keep explaining it then. How many have seen this problem before? Okay, you better say yes, because it's been on the problem set since day one of class. Okay, just checking. So you have a unit square, and you have n points. N could be 50, 100, a million, a billion, a trillion, it doesn't matter. Uniformly distributed, all the points are distinct. They're uniformly distributed in the unit square, randomly. So you get uniform distribution. How many know what a uniform distribution is? I don't want to be presumptuous. Okay, good. I don't have to explain that one. And then you construct a minimum spanning tree, the shortest way to connect them all, to span them so they're all connected in one big tree structure. Yeah. The distances are the geometric distances. So it's weighted, but more than that, it's weighted by the geometric distances, Euclidean distances between the points. No, that's not what the uniform is talking about. The uniform talks about the xy coordinates of all the points without the tree. So without the tree, that's a uniform distribution. No tree. Has nothing to do with trees. In other words, every point in the square is equally likely to occur in this point set as any other point. Equal probability for x, equal probability for y, uniform in both. So every x coordinate of every point is uniformly drawn from the interval 0 to 1. Every y coordinate of every point is uniformly and independently drawn from the range 0 to 1 also, real numbers. Any more questions about it? It's important. It's important to nail down the definitions. Otherwise, what are you solving if you don't know what to solve? Right, So always make sure you understand the problem. That's a good thing to do. All right, uniform distribution, just points, no trees. But on these points, now we impose a tree. Which tree? The minimum spanning tree. Question.
So what does the cost mean?
Cost? This means distance. So the cost of every edge in a tree is the distance between its endpoints, or the nodes comprising that edge. The tree cost is the sum of all those edges, or edge costs, more precise. So the edge between this point and that point is the distance, Euclidean distance between those 2 points. That's all. Nothing more complicated than that. And the cost of this tree is the sum of all the costs of the red edges, which are the pairwise point distances. In other words, if you want to connect all these points with wire, what's the total amount of wire you'll need? If you want to connect all these cities with roads, that means how much cement or asphalt you'll need to build all those roads. That's all it means. Okay. Total sum of distances is the cost of the tree. How many understand the problem now? Oh, good. So I'm glad we paused to define these things. All right. So given a uniform distribution of points, random distribution of points, what's the total cost of the smallest tree spanning those points as a function of n, the number of points? So are we all good on the definition of the problem, what it's asking us to do? Because I can ask some simpler problems, and maybe we should ask some simpler problems first, before we worry about the average or the expected cost of the tree. What's the maximum cost of a tree? If I pick the best tree, what's the maximum cost of such a best tree for the worst case example of points anywhere in the unit square? And this time, they're not uniformly distributed. Make it as bad as possible. Put them deliberately in awkward, inconvenient locations that will maximize the cost of the minimum spanning tree, not minimize it. How many understand this question? All right, what's the answer there? What's the worst possible cost you can have if everything is deliberately placed in awkward, inconvenient positions? First of all, where would you put the points to maximize their interconnect, the total interconnect spanning them? You certainly wouldn't put them right close to each other. You wouldn't just bunch them all up in one square angstrom over in the corner, because then the cost would be almost zero. Let me see that. Yeah. So where would you put them to make it as bad as possible? Put them all in the periphery. If you put them all in the periphery, what would be the total cost of spanning them in this 1 by 1 square? 4. Could it be worse than 4? I mean, you can think of an example where it'd be worse than 4 for endpoints inconveniently placed anywhere you'd like. Is 4 the worst thing that can happen? I mean, say it could be worse than that. Let's say 4 is the worst thing if you're all in the periphery. I mean, say there are examples where it's worse. Well, it's only 2 or 3 people voting. That's incredible. Okay, well, actually, I'm an optimist. That's good, because that means a lot of you will learn something new in the next half hour. Right? So I look at the bright side. There's a silver lining here if nobody's voting. Question? Yes, as a tree. So the points become nodes in the tree, and the edges are interpoint distances. It's a minimum spanning tree. So it's the shortest possible tree connecting those points, wherever they are. So now we're solving the easier problem. Again, we're following Polya's how to solve it strategy. If you can solve a complicated problem, simplify, try to solve the simpler version, and then go back to the more complicated version. Remember last time we talked about reducing the dimensionality of the problem. That's a way of simplifying the problem. So again, we're following straight Polya's how to solve it right out of that book. How many have read the book by now? I don't see all hands raising. So I've repeated that advice maybe a dozen times by now, and still you haven't read the book? Okay, it's your career. So you won't make it to Google or Tesla, but you'll have a okay time writing device drivers for Microsoft for the rest of your computer science career. There's things worse than that. Not a whole lot, but you'll still make your 100,000 a year. It just won't be fun. But I digress. So a bunch of points, you put them wherever you want, make the minimum spanning tree as bad as possible. So we have somebody saying 4 is the worst case. Put them all in the periphery, and then you never have to span more than just the entire periphery, picking up all the points. How many can do worse? What would be a worst case example? Something worse than 4. Yeah. Put one dot in the middle, and all the rest in the periphery. Then how much will that cost you? Certainly more than 4. 4 just to pick up the points on the boundary, plus an extra maybe to pick up the point in the middle. So it'll be 4 plus square root of 2 over 2. Yeah. So it'll be 4 plus 7. Square root of 2 is 1.4142135. I just happen to know that. Half of that is 0.707, so it'll be 4.7. So now we have worse than 4. Can you do worse than that?
But can't we just attach the all point in the center like this? I mean, we don't have to go around the circle in order to connect with that.
But going around the circle will be cheaper than connecting everything to the center. A minimum spanning tree will not do a worse job than it has to. Right? So it wouldn't be like spokes of a bicycle wheel, the center connecting to everything on the periphery like a bicycle wheel spokes. It won't be that. That's not a spanning. It's a spanning tree. It's not a minimum spanning tree. The minimum spanning tree will much prefer to connect everything around the periphery and with one spoke connect one of them to the center, and everything is spanned, but it's a lot cheaper. But that's a nice try. So any other suggestions? So here's the 1 by 1 square. Where would you like me to put the points so that it'll really be bad to span them? So if they're all on the periphery, okay, but we already said the cost will be roughly 4. Put one in the middle and you have to connect one of them to the middle. Okay. What will make it worse? You have n points. N could be large. Yeah.
If you made a grid pattern out of them?
A grid pattern, okay. So you're saying make the points like this, right?
Yes.
Put them in some regular grid pattern. Now when you're trying to span them, what would happen? Try to span those in the best possible way. What would a tree look like on this?
It would cover a lot of the area.
The tree has to reach every single point. So you can have a tree that does this, basically, right? Or lots of other configurations. Right? You don't have to do exactly that. You could do something somewhat similar. You could have used a tree that looks like I'm just making something up. This tree will also do the job and will cost pretty much the same as that tree. How many can see that? Yeah, got the same number of edges, all the edges. Let's say all the interpoint distances are the same as all the other interpoint distances. So this tree and the other tree will have the same cost, right? What is the cost of that tree? Let's say they're all equally spaced from the boundaries and from each other. What's the cost of this tree as a function of n, the number of points? First of all, let's ask a simpler question. Again, following Polya's advice, right from his book, that some of you still haven't read. If the points are all distributed equally spaced from one another, does this minimum spanning tree cost grows with the number of points, or remains constant with the number of points? Grows. How many see it's growing? Yeah. Why can't it be constant? Well, because there's more and more points. You've got to cover more and more distance. You've got to hit every single space. And you'll have more and more dense kind of comb construction. Right? More and more of these spines going on. And there'll be more and more of them as there are more points. And they'll be closer together. And the total tree cost will increase arbitrarily large with the number of points. How large? As a function of the number of points. Give me an upper bound first. Give me some gross upper bound. The tree cost will never be more than how many units long? Guaranteed. I hear somebody whispering n squared. How many say you'll never be more than n squared? How many say it'll be more than n squared sometime? Never more than n squared. Okay, now we have good majority. Why not more worse than n squared? That'll be the area, yeah. It won't be more than the area. But you can find a better bound than that. Also, the area is continuous. The tree is discrete. So when you compare distance to an area, be careful not to compare them head to head like they're both apples, because one of them is an orange. Right? It's like comparing pounds to miles. It's hard to compare the two. One is distance, one is weight. So it's hard to compare area and distance. So be careful. But generally, you're right. It's not n squared. Give me a better bound than n squared for the upper bound and the minimum spanning tree cost and n points distributed any way you'd like in the unit square, not just randomly, not just uniformly, any which way, any possible distribution. Give me a better bound than n squared. Yeah. Okay. Before we even analyze that, prove to me it's no worse than linear. The total tree cost is no worse than linear, no matter where the points are. Linear meaning big O of n. N is the number of points. This one is easy. That's a hint. Yeah.
There are n minus 1 edges in the tree. Each edge can be square root of 2 rather than like 8% square root of 2.
Obi-Wan has taught you well, young Jedi. Yeah. So what he's saying, there's n minus 1 edges in the tree. Each edge cannot be bigger than the square. The square is constant size across at most. One this way or square root 2 diagonally or whatever. So you have n minus 1 edges. Each one is no worse than a constant. The total number of edges add up to no more than a constant times the number of edges, n minus 1. So it's big O of n. How many see that in logic? Yeah, it's simple. Okay. Very good. So we have an upper bound of n of better than n squared, for sure. All right, let's try to improve the n to something lower yet, because n is pessimistic. How could you argue that it's less than n? And by the way, what's the cost of this tree here, generalized to n points? If they're all uniformly spaced, equal spaced from each other, just like a checkerboard, grid pattern, square grid pattern, just like that. What's the total tree cost in red as a function of the number of points n? Okay, I hear some people saying square root. How many can see square root? Okay, just a few. Okay. All right, somebody explain why it's square root. You're right, it is. Why? Yeah. Yeah. So this grid of points, there's n of them. So if you put them in a grid pattern, square grid, and there's n total points, how many points across the length and the width of the grid? Square root of n by square root of n, because square root of n times square root of n is n points. Let's assume that n squared is the square root of n is an integer. So the number of points is a perfect square, just for simplicity. It doesn't really matter. The answer is still the same. It's still square root of n. So square root of n by square root of n. So each span is at most 1 unit length, because it goes right across the width or the length, which are both 1 unit. And how many different spans are there? These horizontal or vertical lines. Square root. Each one is no worse than a constant. Plus one more of the spine to connect them all. That's just one, is a constant by itself. So a constant number of spines, each one square root, square root spines, each one a constant length at most, to a total of big O of square root of n total length. Okay. So this example is no worse than square root. That's better than linear, better than n squared. All right. How many think could be better than square root? Is square root the best we can do here for this example? Intuitively, just what do you think? I'm not asking for a proof at this point. We will prove it too in the next 10 minutes. But for now, you think square root of 2, or square root of n is the best you can do here in red, total tree length, or could you do better than square root? Assuming a grid pattern, the points are fixed on a grid pattern, equally spaced like that, just like a checkerboard pattern. How many say you can do better than square root? How many say no, square root is kind of the best you can do here to connect all these points on the lattice? Yeah, that's intuitively right. Square root is the best you can do. You can try all sorts of other trees. It's not the only tree possible. And they're all the minimum spanning trees. This tree will also be square root. How many can see that? Yeah, because you're just taking the interpoint distances, which are all the same, and you're multiplying by n minus 1. The number of edges in a tree doesn't change. It's one less than the number of points or nodes. Right? How many understand that? So the number of edges doesn't change. It's just their lengths that can vary. But here the lengths of all the edges are the same, no matter how you decide to draw. And obviously, you're not going to connect a point here with a point there. How many can see that? Because each point might as well connect with its nearest neighbor, or one of its nearest neighbors. And you can have several nearest neighbors. So you're never going to have very long edges in a minimum spanning tree, because it doesn't pay to do that. And if you do that, you'll have a tree. It just won't be a minimum tree. It'll be a tree. All right, so we're making progress. We said this is kind of an example. It seems to be square root, and we think it's a worst case example. But that's not a proof. It's an intuition. If the points are allowed to vary at arbitrary locations, do you think that a uniform distribution will be closer to this situation, or will it be closer to a situation where all the points will bunch up somewhere? All the points maybe will bunch up here, making the tree cost almost 0. Or maybe all fall on the boundary by some magic fluke. Right? So a random distribution, will it be closer to this, or will it be closer to something like that? How many say it'll be closer to this, kind of this weird thing here? All right, how many say it'll be kind of closer to this? Yeah, exactly. If you keep throwing darts at a board or at a wall, eventually it'll be all scattered across the wall. There will be darts everywhere on the wall with almost uniform density everywhere if you throw millions of darts at a wall. It's very unlikely that you'll have some scenario like that where all the darts will bunch up around the bullseye, wherever it is you're aiming, or whatever. Okay. This is not a proof, it's an intuition. So you expect random distributions to look more like this. And if you take these exact lattice points, which cost square root of n to span in a minimum way, and you slightly perturb them, you add plus or minus epsilon to every point's coordinates, x and y coordinates, what will be the spanning cost then? Close to what? Say it loud, say it proud. If you take every point in this regular lattice grid and you perturb their x and their y coordinates independently by epsilon, very small amount, plus or minus a few millionth of a unit. What would be the cost to span this new set? Square root of n, or close to it. Very, very close. How many can see that? Yeah. Just take the old tree, keep it on these new points wherever they're going, and the distances are only changing by epsilon. So the tree cost will only change by a few epsilon also, at most. Okay. So most random examples can be spanned intuitively using epsilon plus or minus, square root of n plus or minus some epsilon costs, or more precisely, square root of n, big O of square root of n. The square root of n plus or minus some epsilons is still square root of n. That's an intuition, it's not a proof. We're about to prove this assertion. Okay? How many with me so far? Clear on everything that happened? Okay, good. It's a lot of people, that's great. All right, so now let's say we have a random distribution like we had originally, and we want to span it with a minimum spanning tree. Let's compute the worst case scenario that can happen in terms of this tree cost. Now that the points are not on the grid, but they're just uniformly distributed randomly everywhere, what will be the cost to span them? And already you told me it's a square root, and you're right. Now we need to prove that for arbitrary point sets. And by the way, if it's true for arbitrary point sets, it's true for uniformly distributed point sets. How many can see that? Because uniform distribution is a special case of an arbitrary distribution. It doesn't matter. No constraints. Arbitrary distribution could also be this weird case pathological where all the points are near the corner. That's an arbitrary distribution. It's a weird one, but it's an arbitrary one. If it's uniform, it's a special case of arbitrary. So we'll prove this assertion for arbitrary point sets. So now we need to prove that for arbitrary point sets, no matter where they're placed in the unit square, to span them using a minimum spanning tree will cost you never more than square root of n units of total cost. That's what we'll prove next. And then after that, we'll prove that's true for uniform distributions, not just worst case. And then we'll prove a lower bound, and we'll take it from there. Okay, so for an arbitrary distribution, how would you span them in no worse than square root of n total cost with a minimum spanning tree? How can you show that the cost of a minimum spanning tree is no worse than square root of n? And that's probably the first thing here that's not so obvious as the others. So let's walk through that. Basically, what we're going to do is we're going to generalize this construction that we had earlier, like a tooth comb construction where you do it this way. So what we're going to do is the following. We're going to partition, and we've done this before in other contexts. We're going to partition into n sets of square root of n points each. I'm going to move the points slightly so they're not so above and below each other. Without loss of generality, it wouldn't make a big difference. You know what? Let's do it this way. So there's 16 points, and remember, we wanted the points to be perfect, to be number of points to be a perfect square, and you'll see why that's helpful. Okay, so that's one strip, and that's another strip. Okay, so I'm partitioning the points by vertical strips into square root of n points per strip. And these strips are not equally spaced, if you notice, because they depend on the placement of the points. If you have more points on the left, the strip will be narrower to catch square root of n of them, and the next strip could be wider and so on. How many get this partition? Okay, you'll see in a minute why we're doing this. Intuitively, why we're doing this is we already noticed that the number of points relates to the total maximum spanning length by virtue of square root of n. So square root of n groups of square root of n points may get us somewhere interesting, and so we're starting it to do that. So we're coming up with a general construction of a tree that'll be no worse than square root of n. It won't necessarily be the minimum spanning tree. But if some arbitrary tree that we can construct in general is no worse than square root of n, the minimum spanning tree will be no worse than square root of n either, because among all trees, the minimum spanning tree is the smallest. And that's why we call it the minimum spanning tree, not just a spanning tree. How many understand that notion? So we're going to span them with a tree that's no worse than square root of n, guaranteed. It won't necessarily be the minimum spanning tree, but it'll be an upper bound of the minimum spanning tree, and that will show that the minimum spanning tree cost to span is no worse than square root of n either. Okay, that's the strategy here. Okay, that's where we're going with this argument. All right, so 4 points in each one of 4 strips. That's 4 times 4 is 16. There's 16 total points. Square root of 16, namely 4 strips containing square root of 16, namely 4 points per strip. Now we're going to span them top to bottom in a zigzag way. So we're going to span them like this in each strip, just top to bottom by order of the y coordinates of these points. And then we're going to span the tops of these points with one horizontal spine. So again, this generalizes this construction here, but makes it more general, because that construction works for only when the points are on a grid. Here, this construction works for points located anywhere whatsoever. Okay. What's the total asymptotically, as a function of n, the total length of this tree with these spines? That's what we need to figure out next. What do you think the answer would be, intuitively at this point? We've heard a dozen clues by now. Square root of n. But let's prove that. Let's prove that rigorously. Let's not just wave our hands and say, that looks similar to that, and therefore it's a square root. Maybe it's bigger. And the reason it could be bigger is because you can have, let me show you an example where it could be pretty bad. Right? If you have points that look like this, and then all the other points are here, you know, this partition might look like this, and you may need to span some large partition with a whole bunch of very long zigzags, and you could have square root of n just here. How many can see that? Yeah. And then here you could have even more stuff, and maybe the sum total is worse than the square root of n once you start adding up all these square root of n spans. Because even one span, just this span right here, could be as big as square root of n, constant times square root of n little subsegments. So you have to be careful when you try to prove it. You can't just wave your arms and hope for the best. Okay. But here's what we can do. For every segment, we're going to partition it into a vertical green and a vertical black segment. In other words, we're going to add up all these horizontal and vertical distances. So if you add up this guy and that guy, it'll be less than or equal to this red segment. How many believe that? Just 10 of you? Okay, let me repeat. If you add up this distance here and this distance here, it'll be less than or equal to, their sum will be less than or equal to the red distance. How many believe that? Good, that's a lot. What is that called? 2 words. Triangle inequality. How many see it's a triangle inequality in action? Yes, it is. Okay. So if you add up this distance and this distance and this distance, just the green distances in the entire strip, what's the sum total of all the green distances bounded by from above? 1. How many can see that? Yes, because the squares are 1 by 1. The vertical distances for this strip will be bounded by 1. The vertical distances for this strip will be bounded by 1. So the sum total of all the vertical distances is bounded by square root of n, because it's square root strips. Okay. The horizontal distances could be much larger for this strip than 1. How many can see that? Because the strip could be pretty wide. Remember, you can have examples that look like this. So this could be bounded by 1, this could be bounded by 1, this could be bounded by 1. But together, they could be bounded by square root just for one strip. And there's square root strips. So that can get away from us. So here's what we do next. We extend the scheme, of course, to every single strip. Okay? So we do the counting an alternate way for the horizontal black distances. We add up this distance of the first red segment here with this black distance, with this black distance, with this black distance. Then separately, we add up the second set of distances in black. What's the sum total of this distance and this distance and this distance for all the segments in black for the very first red segment in each strip? The sum total of all the black components is bounded by what from above? By 1. How many can see that? Yeah. And all the black components of the second set is bounded by 1 again. And the third. So what's the sum total of all the black components across the entire setup? Square root of n. So all the red segments are bounded by what altogether? 2 square root of n, which is asymptotically big O of square root of n. And we're almost done. What's missing? The big spine across. This blue segments. We accounted for all the red segments. What about these blue segments? What's the sum total of all the blue segments? At most. Bounded by what from above? 1. Or a constant at least. Maybe a little more than 1, but it's a constant. Actually, you know what? It may not be a constant. I take it back. I mean, see, it could be bigger than a constant. Let me show you how it can be bigger than a constant. You see this example here? What if that thing was the vertical strip? What if the vertical strip, the one in blue here, looked like this? Then it could be more than a constant. But it can't be more than square root of n. Yes, now you're getting it. So the sum total of all the segments here is square root of n at most for the blue, 2 square root of n at most for all the red ones. And so the sum total of this spanning tree, the red and the blue, this generalized construction that we were after, is what asymptotically? Big O of square root of n. So we just showed you how to span an arbitrary set of points in the unit square, arbitrary set of points, by no more than square root of n total distance, total cost of a tree. How many understand what we just did? Okay. And that's huge progress, because that means that a minimum spanning tree is no worse than this arbitrary way of connecting them. The way we connected them is not necessarily the best. It's just pretty good, and it's no worse than square root of n, so the minimum spanning tree is no worse than square root of n also, because it's this or better. Okay. And that's a proof. The logic here is impeccable. And together with this worst case example, that shows you there are cases where it would take at least square root of n, like the regular grid would. There are cases where you would take that much. We already seen that earlier. So for that regular placement of the points on the lattice grid, it will take square root of n. And then separately, this example requires no more than square root of n. That means this result is sharp. Asymptotically, this is an optimal way to connect n points in the unit square. Not precisely, but asymptotically optimal. Not by constant, not the best constant, but the best asymptotic behavior. Square root of n, namely. How many can see that? Because the worst case example matched this general case upper bound. And so this upper bound cannot be improved any further down, because we already have an example that takes that much, specifically for an example. And this example is this method is general. It takes that much at most, no matter where the points are. So we just bounded the worst case behavior of spanning a bunch of points from below and from above by the same quantity, square root of n, asymptotically. Not with the same constant, but with the same functional growth, square root of n. Okay, any questions so far? Because we're not done yet. We're going to go deeper into this now, as if that's not deep enough. Question? Yeah.
What was the lower bound argument?
So the lower boundary was square root of n?
Yeah.
Was that worst case example where they're all on the lattice points? They're all equally spaced?
How do you know that's the worst possible case?
Good question. We kind of skipped kind of the explicit version of this. So how do we know this is a worst case example? How many can see that this example will take square root of n? I mean, we know why, because the interpoint distances are all the same. This is the same as this, 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 the same as that. So you might as well use this distances that we're showing in red, because they're all the same. And it doesn't behoove you to connect a point to something very far away, because you might as well connect it to one of its nearest neighbors. So this does require square root of n. We already know from the other side of the proof that this arbitrary general construction doesn't require more than the square root of n. So this makes this example worst case, because it takes as much as it takes in general to connect points. Right, so the construction we saw earlier always gives you no worse than square root of n. Let me write that down. So this construction is big O of the square root of n. This construction is omega square root of n. Right? This bounds it from below. So together, if it's bounded from above by square root of n by this general construction, and from below square root of n by this specific example, square root of n is pretty much the tight bound asymptotically. And that makes this example the worst case example, because you can never get worse than square root of n by this construction. And here it gets as bad as the square root of n by this construction. So let's be even more explicit. Why does this take square root of n if all the points are placed this way, evenly spaced? Each point has to connect to at least one other point. And the nearest neighbor is already this distance. How big is this distance, by the way? 1 over square root of n. Right? The square root of n, the distance of 1, this whole thing, is square root of n across. So each one of those red distances is 1 over square root of n. It can't be any cheaper, because each point has to be connected to something, and the closest thing is 1 over square root away. And you need n minus 1 edges. So you need at least n minus 1 times 1 over square root, which is the square root, asymptotically. And that's why this example is the worst case. Before, we didn't know it was the worst case. We just knew it was pretty bad. We just knew it's square root of n, but we didn't know the square root of n was the worst case. Now we know from here, because it never takes more than the square root to connect any points no matter where they are, so there are no examples worse than that. because this method works in general. This is a course in algorithms. Is there an algorithm here? How many see an algorithm here between the lines? We didn't use the word algorithm until an hour into the lecture, which is odd for a course in algorithms. But often the algorithms are implicit. And really, everything is an algorithm. Everything you do from the moment you wake up to the moment you go to sleep is an algorithm. Brushing your teeth is an algorithm. Making breakfast is an algorithm. How many understand that? Right? A recipe is an algorithm. So when you cook, you follow algorithms. When you drive, that's a heck of a complicated algorithm. In fact, we're just coming up with algorithms for cars that can drive themselves. It's not easy. Everything is an algorithm. Where's the algorithm here? I mean, it's not a tough question. I mean, it can't be hiding too many places on this one slide, right? The algorithm. Which algorithm? Where's the algorithm? Where's Waldo? Where's the algorithm here? It's not a trick question. It's straightforward. Yeah. Yeah, it's just a construction we used to connect all these points in a spanning tree kind of a fashion. So the algorithm is divide the points into strips. How many strips? Square root of n strips. How many points per strip? Square root of n points per strip. Then span them. Sort all the points within each strip by what? By y coordinate, so that you can connect them high to low by y coordinate. Connect all the top points in every strip to each other in x coordinate order. And by the way, before you partition the points into square root of n strips, what do you have to do before that even? One word? One word? Sort, yeah. How many see a sort hidden here in this? Yeah, of course you have to sort by x coordinate so you can partition them into groups according to the x coordinate order. Sure. So you call a sort routine. It's part of your algorithm. Which algorithm? The one that constructs a tree, like we've shown. So you sort, and then you partition, and then you connect all the things with segments, and you connect all the tops, and there's your tree. So the algorithm is given a bunch of points, construct a spanning tree that spans that point set with cost no more than square root of n total length. It's not prim, it's not Kruskal, but it's a spanning tree algorithm. It's just not a minimum spanning tree algorithm. How many can see all that? And there's your algorithm. And it has a nice guarantee. It will never be more than that total cost. That's a nice guarantee to have. And that's the best we can expect in general. How do we know that? Because there's a worst case example that forces this to be square root of n, and that's the example we saw earlier. So let me ask you a question. If you run this algorithm, this construction, on this point set, what would the tree look like? Like that. How many can see that? Which is what we had before. We just had it sideways, but it doesn't matter. You can take all points and turn it 90 degrees and you get the same answer. Everything is rotation invariant. Right? So this algorithm that we just constructed basically finds this tree for any point set that has this property. Any questions on any of that? How many understand all this perfect? Okay, if you don't understand, ask questions. We'll answer them, yeah.
Is this the worst case for only the uniform distribution or for any general distribution?
He's asking, is this the worst case for any distribution, any locations of points, or just uniform distribution? Good question. How many say, let's crowdsource the answer. How many say, this works for any locations, any distributions, any positions of points whatsoever, completely arbitrary. This still works. There's your answer. It's saying yes. It's arbitrary positions, arbitrary distributions. And this construction still gives you square root of n total length, guaranteed, or less. Does that make sense? Because when we did this, we didn't rely on any distribution. We said no matter where the points are, sort them by x, partition them into square root of n strips of square root of n points each. That doesn't rely on any distribution. This could happen no matter what the distribution.
But then it can so happen that within a strip, some strips have more than square root of n points and some.
He's saying some strips can have more than square root of n points or less than square root. Valid point will make the strips so that have exactly square root of n point. When is the only time that a strip might end up with more than square root of n points, according to this, strictly speaking? So he's bringing up a subtle point. It's a boundary condition. When can you have more points than you need in a strip? If you start partitioning it by x coordinates, counting up the square root of n, and another square root of n, and another square root of n bunch. If a bunch of points vertically are right above each other with the same x coordinate, if x coordinates are not unique, you could have a problem, potentially. Is that what you're getting to? Yeah, very, very valid point. How many see it could happen? Yeah, and then what do you do? So break ties by y. In fact, you can do better than that. Break ties arbitrarily. So if a bunch of points fall on the same line, make some of them go into one strip and one of them go into the next strip, and that's okay still. Let me give you another way to handle this. This is a little more subtle, but it's very general. To avoid the cases there are points right above each other, vertically, with the same x coordinate, add epsilon, plus or minus epsilon, to the coordinates of every point that has this problem. Make every point epsilon larger in x, or epsilon smaller in x. Then you won't have that problem anymore, if it's random epsilons. Pick different epsilons for these points. So if some points have the same x, make one of them move them slightly over epsilon. Move the next one 2 epsilon, the next one 3 epsilon. Now they don't have the same x, right? How many see that? But the tree will be almost the same, plus or minus a few epsilons. Make epsilon a googolth of a millimeter. No big deal. It's essentially a tie-breaking scheme. You don't really have to do the epsilon. Just break ties arbitrarily, which is what I said earlier. But with the epsilon, it's clear to see that that works. Good question, subtle answer. How many can see that, what just took place? Yeah, very good, means you're thinking. What else? Anything else? Issues, boundary conditions, special cases? Yeah.
So the expected or average one times of like constant the same distance.
So we haven't done the average yet, that's the hard part. Everything we did up to now was the easy part. We're getting to the real question now. On average, what happens? Because, you know, this algorithm shows you it never takes more than square root of n. This example shows you it sometimes does take square root of n. So the algorithm is sharp. But that doesn't tell you what happens on average. How many can see that? Yeah. It's just like quicksort. Quicksort will never take more than quadratic. Okay. And there are examples where quicksort will take quadratic, but never more than quadratic. Does that mean on average quicksort takes quadratic? No, it doesn't. Same here. This shows you it never takes more than square root of n. This example shows you sometimes it's as bad as square root of n, but on average it doesn't mean it's square root of n. Just like quicksort. Or any other scenario where you have a max and you have a worst case. The average could be the same as the two, or it could be much less. In quicksort, what determines whether it's quadratic or not is how sorted the input already is. Because when it's completely random, it takes closer to n log n. When it's sorted or almost sorted, it takes closer to quadratic. So the question is, for arbitrary permutations of numbers, are they almost sorted, or are they mostly random? And the answer is mostly random permutations. Very few permutations are actually sorted. There's n factorial permutations, and only two that are actually completely sorted. The monotonically increasing permutation and the monotonically decreasing permutation. Any other permutations are not completely sorted. These two extremes take n squared time. All the rest take less. So the average is much less than quadratic for quick sort runtime. Same scenario here. Most distributions, will they look like this, or will they look like something much more pathological that requires a much shorter tree overall? How many say most distributions will look much closer to this than to some pathological example that takes a lot less than the square root? How many say most of them look like this? Random, uniformly distributed point sets. Yeah, most of them do look like that, scatter plots. But that's not a proof. That's an intuition. It's a correct intuition, happens to be, but it's not a proof yet. We're about to prove this. So here's how we're going to prove this. What we're going to do is partition the point set into square root of n strips in both directions, but equally spaced now. So these are equally spaced. So each square is 1 over square root of n by 1 over square root of n. So they're equally spaced squares, like a checkerboard. And what we're going to do is focus on one of these squares. So one of these squares is just, I'm blowing it up down here. On average, a large number of these squares will be occupied by points, as opposed to being empty of points. How many can intuitively see that? Not a proof, intuition. How many squares are there, by the way? There's n separate squares. Square root of n this way, square root of n that way. So there's n points randomly placed in n squares, or n boxes, uniform distribution. So it's like having n containers, and I'm going to take tennis balls and put it in a random container. Take a second tennis ball, put it in another random container independently of the first, and so on and so on. At the end, many of the containers will contain a tennis ball. How many can see that? Yeah, they won't all bunch up in 1 or 2 containers, obviously, because I'm putting them uniformly distributed. How many can see that it's also unlikely that all containers will contain a tennis ball? That's also unlikely. Why? Intuitively. What would have to happen if I put n balls in n containers for every container to contain a tennis ball? It's not very likely. It means nowhere in this process will 2 balls go into the same container. Otherwise, one of them will be empty at the end. Okay. It's similar to the pigeonhole principle here, okay? But a probabilistic version of the pigeonhole principle. Right? So the first ball will go in an arbitrary container, the second one will go to an arbitrary container, again independently of the first, and so on and so on. The chances are that no container will be hit twice in this whole process is also relatively small. The chances are that all will fall into the same container, or the same 2 or 3 containers, is also small. So what portion of the containers will contain both? We'll come back to this question. But here's what happens when you have a point inside one of those little squares. If you have at least one point inside the square, and this square is of this size, even if it was just a 1 by 1 square, if you have a spanning tree over all these points, and one of them is like this. One of the edges of the spanning tree will have to go from a neighboring cell, hit that point, and then exit it. But either way, that point will be have to connect it in the spanning tree to at least one of the boundaries so that it be connected to some other point outside this box. How many can see that? So there'll be some contribution to the minimum spanning tree cost based on where this point is located in this square. Because that's a piece of the edge of this spanning tree that spans the entire point set. That piece is what this point is responsible for, at least. And even if it's connected not to an arbitrary edge, but to the closest edge, the question becomes, how far away is a point on average from the closest wall of this square in the probabilistic sense, when it's uniformly distributed somewhere in this square? On average. And once you compute that quantity, you can multiply it by the number of squares that are occupied after this experiment putting n balls in n boxes. And the product of those two will be a lower bound on the expected case for a minimum spanning tree cost as a lower bound asymptotic. How many can see the strategy gelling together? Okay, a few people. I'll take that for now because we're not finished. What's the average distance of a point? Let's simplify it. Let's make it a 1 by 1 square, and you have an arbitrary point. How far is that point on average, if it's uniformly placed, from the closest edge? How far is this point from the closest edge? Is it on average 1 unit large from the closest edge? How many see it can't be worse than 1, obviously. And the whole thing is 1. I'm talking about the closest edge. In fact, it can be worse than what? You can come up with a better upper bound than 1. 1/2. I mean, you can see 1/2 is also up, because the closest edge will be no more than half the distance of the size of the square. And the size of the square is 1, so the closest edge will be no more than 1/2 away. Could it be 1/10, 100th of a unit away? In fact, the only place where it'll be as bad as 1/2 will be where? Right in the center. There's only one place where it could be as bad as 1/2 in the center. All the other places will be a lot less than 1/2. So the average will be what? 1/2 or less than 1/2? A lot less than 1/2. How much less than 1/2? Take some guesses. What do you think the average distance would be? How many? It will be a millionth of a unit? How many say a millionth or a billionth or 1,000th of a unit? How many see it's too small? Nobody's saying anything. Okay. Well, you tell me, what do you think the average would be, roughly? You're standing in the room, anywhere in the room. The average distance of you to the closest wall is what, as a function of the size of the room? Let's say the room is a 1 by 1 normalized so that we don't have to worry about arbitrary sizes. You could always shrink or enlarge that quantity proportionally and you get the same answer. How many can see that? So without loss of generality, assume it's a 1 by 1 room. 1 unit this way, 1 unit that way. How close am I to the nearest wall if I'm in a 1 by 1 room? We already said 1/2 is the worst if I stand right there in the middle. Quarter? How many say a quarter? We say less than a quarter. Something different than a quarter. How many can see it's not anywhere near a 0? Yeah. I mean, I can be lots of places in the room, but I'll very rarely be so close to a wall where I'll be close to 0. That's a very rare case. Most of the time I'll be somewhere off the wall, close to the middle, somewhere in the middle vicinity, somewhere. It'll be a lot larger than 0. How would you compute the average? Let's just take that as a sub-problem. Interesting. So he's suggesting that if the minimum is 0 and the maximum is a half, maybe we should take the average of 0 and a half and it'd be a quarter. How many say, yeah, that's right? We say, might be an issue with that. So split vote, nice. What could be an issue with that? It's a very good try. Yeah.
So visually, it seems like that it's a quarter is making the assumption that they'll be generally clustered within an internal ring within the square.
Yeah. There could be a lot more closer to a half than to 0. And that'll skew the answer. So let me use your logic with quicksort, just so you see how it fails. Quicksort runs in maximum n squared time and minimum in n time. So the average of quicksort runtime is n squared plus n over 2, the average of the two, which is n squared over 2, roughly. QED. What's wrong with this logic? Obviously, it's not correct. Because there's a lot more cases where it runs in very low time than very high time, and those pull the average down. Okay? So you have to be careful. It's a nice try. I mean, sometimes it works, actually, what you said. But sometimes it's skewed, and you have to account for that skewness. Here it's also skewed. What else? Average distance from the closest wall if you're in a 1 by 1 unit square. How would you compute it? What techniques will you use?
You can just add up all the points that are close to, let's say, a unit distance from 0, then how many are close to 1 and 2.
Yeah. How many are closer to 1, how many are closer to 0? But there's an infinite number of possibilities. So we have infinite numbers of possibilities. You have some function. The function is the distance to the closest wall. It's a two-variable function on x and y. How many can see a two-variable function? That's the distance to the wall based on x and y. Two-variable function here. How do you come up with an average value of a function over one variable, over two variables, over any number of variables? What is that field called? What mathematical field gives you averages of varying quantities? Calculus. How many can see calculus? Yeah. And in particular, within calculus, what is it called, this technique or this quantity? That's the average value of a function over a range. It's called an integral. How many heard of such things once? Okay, good. So it's the integral over this function with x and y. It's a double integral on x and y. How many can see that? Yeah. But this is not a course on calculus. This is a course in being rational, being a problem solver, being a MacGyver, right? So the average distance, let's say, as x varies, the average distance will be 0 near the boundaries, and the distance to the nearest wall will be half over here. So the function, as a function of two variables, the surface, right, z is equal to maximum distance of x and y, coordinate point, will look like what? The surface will look like what over the xy plane? Let me draw it in perspective for you. This is a 1 by 1, right? And if you're in the middle, the distance will be a half, right, to the nearest wall. And if you're at the edges, the distance will be 0. And the distances will increase as you get. So this function will define a surface that will be a pyramid, right? The distance to the closest wall will be half at the very center, and it'll drop to 0 at the boundaries of this 1 by 1 square, uniformly and linearly. And that describes a pyramid, a 1 by 1 pyramid with height 1/2. How many can see that? Good. And so in terms of this pyramid, the answer that we're looking for is what in terms of this pyramid? It's the average height of the pyramid, right? Is it the answer? How many can see that? Yeah. What is the average value of a function over an interval. You already told me it's an integral. But it's also something else more intuitively, colloquially. Thank you. It's the area under the curve. When you take an integral, you're taking the average value of a function. But it's also the area under the curve. It's the average value of the function times the length of the interval. If you take the average value, multiply it by the interval size, that's an area. That's what defines the average, actually. It's what you have to multiply by the length of the interval to get you the total area, and it's the average value of that function over that interval. And that's also called an integral. That's what integrals are. It's average values of a function over an interval. In 2D, what is an integral? What's the 2D generalization, the next dimensional generalization of an area? A volume. So if the base is a 1 by 1, you're looking for the average height of the pyramid, which means whatever the base size is, 1 by 1, times the height will be the volume of this pyramid. The area under the curve is a volume in 3D. It's an area in 2D, it's a volume in 3D. It's a hypervolume in higher dimensions. So now we're looking for the volume of this pyramid. How many can see that? That'll be the average distance from the edge. And we're not using integration. We could use integrals. We won't, because you can do it without integrals. What's the volume of this pyramid? It's a 1 by 1 by 1/2 high pyramid. What's the volume of it? And you know me by now. I don't expect you to integrate. I don't expect you to memorize a formula from high school algebra of the volume of a pyramid. How would you determine the volume of a pyramid 1 by 1 by 1/2? Without remembering a formula. How many know there's a formula for this? How many know the formula for this? That's what I thought, just a couple of people. So obviously, we're not going to go there. Yeah, of course there's a formula for it. Remember the staircase? Red and blue. Flip it over, you get a square. Do the same trick here. Be a MacGyver. What's the area of this?
1/6.
He says 1/6. How many see a sixth? Yeah, a few people. Why a sixth? Somebody else. Why a sixth? Why a sixth? Because there's another pyramid here in blue, and there's another pyramid, and all these 6 pyramids, 4 on each side plus 1 on top, together make up what? A cube 1 by 1 by 1, and they completely fill up that space. Because that point, the apex, is a half in, a half in, and a half in all 3 dimensions. It's the middle of the cube. All 6 pyramids meet in the middle. The cube is 1 by 1 by 1. So 6 pyramids, each pyramid is 1/6 in volume, and that's your answer. So a point, uniformly distributed in the unit square, is 1/6 away from the nearest wall on average. And we did this without calculus, without integration, without a formula for the volume of a pyramid. We just did it intuitively, and that's the correct answer. If you do the double integral, you'll get the same answer, 1/6. Very good. Extra credit for saying a 6. And of course, we're not done yet with the original problem. That's just the average distance of a point to the nearest wall is 1/6. But of course, you can sort of tell where this is going, and next time we'll finish it off. But for extra credit, this is still extra credit, finish off this argument. Show me that on average, the minimum spanning tree cost of endpoints distributed uniformly in the unit square is square root of n. Not less than that. And we know it can't be more than that because we have a general construction that's never worse than square root of n. But there's still enough meat here for extra credit. The next time we'll finish it up. Any other questions, comments? Those of you that worked on the midterm, what do you think of the midterm? Yeah, all the problems were very familiar. They all came strictly from the problem set. All 7 problems came from the problem set, verbatim, as I promised. So you've seen them all before. Hopefully you solved them all before. And when it came time to the midterm, you just had to write down the answer and walk away in 20 minutes. That's my hope. Okay. So very, very fair exam. Just like I said, the final, same thing will happen in the final. Okay? Yeah, question?
Are we getting a different set of concepts for the final or just those concepts?
That's the posted one. That's it. Final will come right out of those, just like the midterm. No tricks. I say what I mean what I say. All right, see you next time.